Lauren.
Hello.
Hi. I'm just
Oh,
sorry.
hi,
I'm just
Jesse.
doing the register. Hi, Naomi.
You are now
And
muted.
Ash, putting you. Rida, welcome, Rida. And Safi, I've got Safi on there. Hi, Liz. And Ellen. Justin, got Lawrence on there. No, nearly forgot Lawrence. Right, okay, got Lawrence on there. Okay, right, I think I'll start. This is the first time our lessons start really close to the time it's supposed to start. Wow. Okay, right. If you need me to stop, you can turn on your mic and say, "Oh, I have a question." Okay. If that gets too cluttered with too many people getting me to stop, I'll try and slow myself down. Oh, welcome, Piers. What I'll do is, I will then stop, and then you can say whatever it is that you need to say. Okay, so we are doing chromatography. You have done some chromatography before, but this will be a little bit different. Okay, so we're concentrating on something else. This type of chromatography that we're going to do, we can't do because we don't have the equipment. It's all very high tech. Okay, so the chromatography that you've looked at before, if we have a look, is a separation technique, and it relies on the solubility or the affinity for a mobile phase and a stationary phase. Okay, so far, no, Yasser, it's not the orange booklet. This is a different PowerPoint, but I will be moving on to the orange booklet in a little while. But I just wanted to go through the PowerPoint first, and then we can start filling in the orange booklet together. Okay, and so this is the mobile phase. And the mobile phase is the thing that moves. So it's so far, if we remember the basics that we've done, I don't know if you've done this, but we've got a. Yes, Holly, it's the booklet. I sent it by email as well, so you should have it on an email as well. Sorry, some people worried about their
Has
orange
it
booklets.
got like an orange back cover? Because I've only got the one with, I think that's the one I've got, but I don't think I've got the orange one. Is it a completely separate booklet?
No, it's.
Oh, okay. So I've got the book
With
anyway.
the orange front
Thanks.
cover. So you've got the right book, but it's just when I printed them with an orange cover.
Oh, okay. Thank you.
That's okay. Right, okay, and then right, so we've got mobile phase and stationary phase. Usually we've been doing thin layer chromatography or paper chromatography. So these two here. So in the paper chromatography, the stationary phase is the paper, and the mobile phase is the solvent. Usually you use it as water. Okay, but in thin layer chromatography, the stationary phase is your plastic plate with the silica on that's been sprayed on top of it in a very thin layer. So we did this the week before we broke up anyway, so that's fun. So we've covered all that. You know pretty much the basics. You've done it lots of times, right? And then we have two other types of chromatography. Something called high performance liquid chromatography and something else called gas chromatography. So I'm going to move on to the gas first and then go back to the liquid because they're a little bit different, but they're also quite the same. Okay, so we've got some similarities and differences there. So the mobile phase is the phase that carries things through. So usually it's been a solvent and it carries your components of your mixture up whatever your stationary phase is. Your stationary phase is the bit that stays the same, so it doesn't move, and the other mobile phase moves through it. Okay, pretty straightforward. Okay, and then we've got paper, thin layer, or TLC, which is what we've been doing, and this high performance chromatography. And the high performance chromatography used to be called high pressure chromatography because you use pressure to force things through the solid phase. Okay, and then we've got gas chromatography. There are some more, but we don't need to look at them, thank God. Right, okay, basic techniques. So we've done basic paper chromatography. You would have done it in primary school, I think, some of you. Right, and excuse me. It requires a sample for preparation. So you might have done inks in your felt tips. It's good for separating water-soluble inks, and there's a limited type of mobile phases because not everything is soluble in water. Also, it kind of requires you to have quite large molecules that are visible. Okay, so it's quite slow. You either use a naked eye or UV light. If you've got a very small amount of sample, it won't work. Okay, just get lost in the paper. Okay, so thin layer chromatography is basically the same technique as paper chromatography. It's an improvement. So we always use the silica gel, but you can have an alumina, which is aluminium oxide based one. No, oh, sorry. Okay, and you can have acid, basic, and neutral components that can be separated. Right. The solvents are varied. You can vary depending on what you want to separate. You can vary the components. You can have them in different combinations. You could have an organic solvent if you want things to be very soluble. You can mix it with a polar solvent if some of your molecules are polar, etc. So you sometimes you need to do a bit of trial and error to get the right solvent mixture to separate your substances. So it's good for monitoring the progress of a reaction. It requires very little amounts. Identification of components in a mixture. Purity determination, because you can measure the RF values, and you all know how to do that. And conditions for column separation techniques. So you can adjust the conditions. You can do it in a warm situation if you want it to be faster. It always needs to be airtight because you don't want the solvent evaporating. Okay, it can be semi quantitative, so you could measure. If you do it very accurately, you could scrape off your silica gel on your spot and get back some of the component and then measure how much you got back. It's pretty tricky to do, but it can be done. It's usually quicker than paper, depending on the phases. You can use chemical spray, iodine tank. So if you might have heard of nihydrin, so there's nihydrin, which is a chemical spray that you spray on and then your spots become visible. And you can use UV light. Okay. And we've done this before, and look, that's what it should look like. It's never ever after 10 minutes. I don't know what made them think it would be 10 minutes, but okay, usually takes about half an hour. It's solvent slowly goes up. Usually, we can't really see anything there. Okay. Usually they're clear, and then you can use. We tend to use the iodine for our stuff, don't we? Okay, and then you calculate your RF values. We've all done this before. Distance travelled by component divided by distance travelled by mobile phase. You label the top the solvent front, and then it's this distance divided by the distance that the solvent travelled, and you get a value. The value varies. The lowest value can be 0 if it hasn't travelled at all, or it can be 1 if it's travelled right to the top of the solvent front. If it's travelled right to the top of the solvent front, that should not be happening. Okay, that means that you've got the wrong solvent or the wrong stationary phase, and it shouldn't travel completely up. But usually it's a decimal number between 0 and 1. Okay. Right. And then we have performance liquids, high performance liquid chromatography. Okay, in this, your mobile phase are solvents, water, or mixes of the two. Sorry, hello, Josh.
Hello.
We've got something to say.
Welcome. Sorry to be late.
Sorry, right?
Oh, that's okay. Yes.
Are we going through the booklet?
Yes, we will. But I want to just give you an overview.
Okay.
And I'll share the PowerPoint with you as well. I'll send it to you by email.
Okay, thank you.
Okay, don't worry. So I'm just going to go through this so that we have an idea of what we're talking about, because I think the booklet goes into a lot of detail very suddenly.
Okay.
And if you don't have a kind of overview, it can be overwhelming.
Okay.
Okay. Josh.
Hello.
Hi. Right. So I gave out a booklet which you may or may not have on the
Yeah.
last day, which was orange.
I do have it, just not with me right now.
That's okay. If you've got a piece of paper, you can take some notes.
Okay, but are you sort of going through it now? And then
I'm not going through it right now, but I will go through it, but in parts, so it'll be quite slow. So even if you've got some paper, you can jot down bits while you're going through. Okay. Okay. This is going to be quite a short lesson to get us started, and then I'll give you a task. You can go away and do the task. I'm going to continue just for everybody now that I think most people have arrived. Is that what I'm going to do is I'm going to give you slightly shorter lessons and send you away with a task. I'm intending to have the lessons at our normal lesson time. And the reason for that is if I put you at a different time, it'll get confusing with your other lessons and your other teachers. So I want to avoid any confusion. Does anybody have any questions right now? I'm going to pause a second. You can put your mics on if anybody's got any questions or they want to ask anything.
No.
We all okay? Okay, cool. Oh, okay, all good. Right, so please do speak if you have. Okay, thanks, Josh. If there's anything else, you can just pop your mic on or type it up. It's fine. Pause me if I'm going too fast or if you think you're about to fall asleep. Okay, because I think I'm more worried about that than anything else. Right. Okay. Right. So, in high performance liquid chromatography, you have a mobile phase that can be solvents, water, or mixtures. Okay. Now, the stationary phase is a little unusual. It's silica based and it depends on the application and what you're doing. So it can be gels, and you would have used the gel, I think, when you did the DNA separation. Did you all go to Oxford University for the separation? Yeah. Okay, and that is a type of performance liquid chromatography. So actually you've got a gel and the liquid's being forced through it. Okay, so it is quite complicated. It requires sample preparation, and it's normally done. Okay, there's different types, so they're all done slightly differently, but in general, you have precise injected volumes that you're putting in. You can control the composition and the flow of the mobile phase. You can push it through faster, you can push it more slowly. Okay, it's conducted in an oven, so you can control the temperature where it's happening. And it's very widely used in analytical laboratories. Okay, you can quantify components. That means you can here's a mixture. My mixture was, say, 12 milliliters. 4 of those milliliters were component A. 6 of those milliliters were component B. So you can be very precise. Okay, it works really well for non-volatile mixtures. Now, volatile means something that becomes a gas easily. Like when you go to a petrol forecourt on a summer's day, you can smell and almost see the petrol. You can smell it from further away. So anything that's volatile becomes a gas very easily. This also means that you can use solids. Okay, so things that are non-soluble. So usually when we do TLC, we dissolve things in ethanol and they're quite soluble, but things that are completely but in TLC we always avoid getting any of the solid onto our TLC plate. But here you can actually use solids and you can separate solids out too. And it gives you retention times. So it's different to TLC retention times. So when you inject your sample, you work out what time you put it, do you time it from when you put it in to when it reaches the detector. Okay, so, and then there's gas chromatography, has a mobile phase, which is an unreactive gas, has a solid phase, which is a polymer or liquid on a solid support. You have, you can prepare your samples, you inject precise volumes, you can control the temperature and the gas flow, whether you push it through faster, what temperature you're pushing it through. It's used in analytical laboratories, and you can see quantify means you can count volumes of how much you've got of the substance. It uses volatile mixtures, so this is different to TLC plates. TLC plates want soluble things. The high performance liquid chromatography wants can do solid things and things that are non-volatile, but this gas chromatography uses volatile substances, so things that become a gas easily. If they are big or long molecules or polymer molecules, they are hard to make into gases, so you can't use gas chromatography for them. You have to use the high performance liquid chromatography. Okay, and this is what the columns look like. Okay, so the columns are long tubes, hollow tubes, and they're coiled up. So you can make them really, really long, and they allow for really good separation, because the longer it takes them in the column, the more likely the molecules are to get further apart, which allows you, then you can actually have precise volumes of sample. So this mixture is made of 14 molecules of this and 20 molecules of that. So really precise things that you can do with it. Okay, and sometimes you can change the size according to what you're separating. So it's really good. An industry, depending on what you want to do, you can do different things. Okay, so it basically looks like this. Okay, so there's your column, there's the sampler, it takes the samples, there's the injector, injects it into the column, goes through the column, comes back down to the detector, and the detector gives you a readout. Now that looks really old, that computer. Okay, so we have a look. So there's different types, each one will be slightly different, but they'll all have the same things. They'll have an auto sampler, so it's all done robotically. The injector, so measures the volume, puts in a precise volume, or if it's a solid, it measures it precisely, puts it in, goes through the column, goes winding round, and goes up to, reaches the detector. The detector then gives you a printout. Okay. And obviously you can adjust the pressure, you can adjust how fast it's going, you can adjust the temperature, that's all done with the keypad. Okay, right, and that is the end. Right, there we are. So you can start, if you're making things, you can sample them at each stage to make sure that you've got the samples that you wanted. And this is what your chromatogram looks like. So in a gas chromatography, it looks like this, really. It's really, really unusual. Okay, it looks a bit different to the graphs that we've done. So they've got a large gap here, and that tells us something about how we're going to measure how much our substance that we've got, and it tells you which peaks and the time. So it tells you how long it took for them to reach the detector. Okay, so we're expecting that you should have some predictive software. There's usually databases, and you're saving resources because you're not printing things out. It does a lot of the assessing for you. The area under the curves here, or these peaks, the area under the peaks tells you the amount of that particular substance. So it does the calculating for you. Okay, so there we are. Okay, right. And then I did, how do I get rid of this? And then I did have, no, not this one. I'll get rid of that one. All right. Now I'm going to try, I did try earlier. Upload a presentation. So this is the one that I want. Okay, how do I get rid of this one there? Okay. Oh, there we are. Right, so this should be your booklet, she says.
Is that the orange one?
Yep.
Okay.
Right, so how do I get it? No, I don't know how to get it up. Yeah, that's my current one, but I can't see it. Okay, confirm. Right. Okay, this is interesting. Oh, there we are. Right. Okay. And oh, I can't. Oh, I can increase the volume. Oh, size, right. Whoops, that's not what I wanted to do. I was hoping the whole page would increase in size. So that's what the booklet should look like. Is everybody okay with that?
Yeah.
I've emailed most of you with a copy as well, so you should have a copy somewhere. Okay. I realise that I've been talking for 20 minutes non-stop now. Right, so 1 minute.
You are now. Hello, everyone.
Hi, everyone. Who is that? Is that you, Josh? Welcome. Right. Okay, so I hope you've got your booklet in front of you, and I'm hoping to do some writing on it, but I didn't realise it was so tiny. If I do that, what happens? Right, can you see that?
Yeah.
Yeah, because I can't see your typing anymore. Is it big enough to read? That's my question. So let's have a look, and if not, we'll have to find some other way of doing this. Right. Okay. Right. So can everybody see this? So we're going to start with gas chromatography because you have to compare the two in your assignment. Okay. And there we have a carrier gas. So we supply our gas. You have the injection port. All of this should be automated, really. Okay. So your sample, I have no idea what's happened to it. It's all gone funny. Right. So your sample is introduced here at the injection port. You your column then does the separating, and because it's in an oven, you can control the temperature. And then once your components of your sample reach the detector, it then interprets it for you, so you get a reading or recorder, and it plots it for you. Okay. In the gas chromatography, you have a liquid on a solid support, so you have a thin layer of liquid. Usually, but not always, a long-chained alkane. So if you put your microphones on, can somebody tell me why we'd use an alkane?
I have no idea.
Anybody got any idea?
Alfie, this one's for you.
You are now unmuted.
I don't know.
You are now
I don't think
muted.
anyone knows.
Nobody knows. Okay, alkanes are really unreactive. Okay, so when we went through organic chemistry, right, long-chained alkanes make. Oh, sorry. Someone's saying something. You can turn your microphones off now. Okay, right. So long-chained alkanes are really unreactive, and that's the reason. So you might, so if I write it there, right, oh God, right, I've got to get it to work now. Right, let's see if I can get this to work. And you can write, okay, don't write it all over the diagram. I'm sure yours will be neater than mine. Okay, and they're used because they're unreactive. And that's the, so long chain alkanes make things like plastics, and plastics don't do anything. You put acid in them, you put alkali in them, in general, they don't really do anything except burn. Okay, that's the only thing they're good for, really. Okay, and then it's coated on the inside of some of the capillary tubing, and it can be up to 30 meters long. You can change it and adjust it to your needs. Okay, so change and adjust. Sorry, my terrible handwriting. I think that's an A that I was trying to write. Okay. So it acts as an inert solid support. So inert just means unreactive. This is called a gas chromatography column. Okay, even though it's not actually a column, it's a tube. Okay, and then the mobile phase, on the other hand, is an unreactive gas called a carrier gas, which flows through the column. So usually argon. So argon's a really good example. I've forgotten, is it AG or AR? I'm going to write it. Okay, it's usually argon. Okay, and because it's readily available and it's very unreactive. Okay, and then that's what it looks like. So if you cut a hole in the tubing, you'd have the solid on the outside, solid support on the inside, and then the stationary phase, which might be a gel, might be a liquid, very thin layer, a bit like when you coat your frying pan with oil. Very thin layer of oil, maybe, because that's alkanes tend to be oils. Okay, and then what happens is you inject your port. The molecules are a mixture there, so when you put them in, they're all mixed up. And then what happens is they are pushed by the carrier gas. And they go through the column, and they're pushed and pushed. And what happens is the lighter ones, the ones that are not as sticky or attracted to the stationary phase, move faster. And the heavier ones, or the ones that are more attracted to the stationary phase, are slowed down. So they're usually what we call retarded, which is quite rude, but it usually just means that they're kept back because they're attracted to the stationary phase. And they go through and eventually they separate out. And actually, this is probably not a very accurate representation. The longer your column, the bigger the gap between them. So then we'll find that the most volatile things separate out first. And so I'm going to say this thing here, it'll all look like one color, but that is yellow molecules. Are most
What do we put? Do we just write down the smaller molecules?
No, yellow ones, the ones that are first to reach the detector. So should I start typing? I'm wondering if I might try.
So have we
No,
got this in for our assignment?
I beg your pardon, sorry?
Are we filling this in for our assignment?
For your assignment, Rosie and I haven't quite decided what we're going to do. We're kind of teaching it to you, and then we're going to see what the exam board say. They haven't sent us any information yet about what they want us to do.
Is this for the assignment there?
Yeah, but it is. If we were doing an assignment, this would be for the assignment.
Okay.
So I'm trying. It is actually a research assignment, but I'm trying to give you some background and basic information so that you can get started. Because obviously, normally we'd try and do a lot of it in class, but obviously that won't be happening. So I'm doing it here instead.
Are you going to email us PowerPoint?
Yes, I will email you the PowerPoint. If I don't, just send me a reminder email. And so now, usually I work part-time, but now I'm kind of working throughout the day. So even if you email in the evening, you might get a reply that same evening.
Okay.
Okay, cool. Right, so yellow molecules are most volatile. Okay. Oh, I can't even get it to write. Volatility. Okay. And now I've got the background noise. Right. Is that okay? Oh, what's happened? Can't hear anybody.
Wait, so should I put
that's good.
nearer
good.
to the detector is more volatile?
Yes, so the first ones to reach the detector. Okay. Oh God, my handwriting's gone bonkers and it's not detecting properly. Oh, I got rid of everything. So I didn't intend to get rid of everything, but I don't know how to get it back either. So, First, so can't get an R. First to reach detector. Okay, that looks terrible, but never mind. I'm sure I'll improve as we go along because it's the first time I'm doing it. So, oh dear. Right, okay. Any more questions? It's gone deadly quiet. I feel like there's nobody there.
I'm still here. I don't
Okay,
have
good.
No,
Right. You may speak,
You are now
people. You may
unmuted.
speak.
You are now muted.
Hello.
It's so weird because I can't see anybody. I'm just talking into the middle of nowhere. So, no, it's nice to know you're all there listening. No. Okay, I'm sorry about my writing, but I'm not quite sure what I can do to fix it. But I'll need to find
Alright,
some
it's just
way to
about
fix it.
readable.
Just suggested OF4.
Sorry? What did you say, Alfie?
Was it Alfie or Lawrence?
I think
Oh,
You
I-
are
that's
now
Lauren.
unmuted.
Oh, sorry. What were you saying, Lawrence?
You are now muted.
What were you saying, Lawrence? Nothing, apparently. Okay. Right. I'm still getting to grips with how to use this, so this is interesting for me. Like, what's okay? I don't want to press anything in case everything disappears. Right. Okay. I'm just going to turn the page. Right. Okay. So, what information does it give you? So I've told you how you do it. Right. This is how you do it. That's what makes it works, having a stationary phase and a mobile phase. But actually, what does it tell you? So it gives you something called retention time. Retention time is the time it takes for your component, you injected it, the time it takes from when you injected it to when it reaches the detector. Now, depending on exactly which equipment you're using, it can be done in minutes and seconds. Okay, so minutes and seconds are the times we're talking here, whereas R1 takes quite a long time. Okay, when we're doing TLC, it's quite slow actually, isn't it? Okay, and then different compounds have different retention times. Unknown can be compared with a known compounds for identification. Okay, so you have a database and you can compare it just like RF values. Your spots for paracetamol and the unknown should be in the same place. It's your retention time should be the same. And they'll, because it's all done electronically, there's a database and they would compare whatever you're comparing with the database. So say you were doing blood samples and checking if someone was over the alcohol limit. So what you could then check how much alcohol, if they've got any alcohol, so they'd have some ethanol. Let's see, that's number 2 there. So they'd have some ethanol in their blood and you could check how much there was. Okay, and this would tell you, and they tell you exactly how much. And this is what they use to check the blood alcohol level. And then this could be used in a court of law. Okay, right, so different compounds have different retention times. Okay, so area under the peak. So you get retention time, which helps you identify the substance. So that is for ID, the identification. And then area under the peak, sorry about my terrible handwriting in advance, tells you how much. Okay, so it tells you how much of the sample that is that particular component. So proportional to the amount of component in a sample. It can be used to find the quantity of a component provided standards with known quantities are used. So the same that you use for say colorimetry, you'd have a standard that you know, you make that up, say 1 mole per decimeter cubed, you put it through the system, you see how long it takes and how much volume how much area under the curve it gives, and then you put your sample through and you see how much is that area, compare it, and it tells you how much you would have. Okay, Right, so there we've got a gas chromatogram. Now I'm going to try and enlarge it and see what happens. Okay, and well, not very well enlarged because it comes out of the screen. What if I do that? Oh, no, we've gone back again. Right, let me try again. Okay. Right, so if we have a look, right, so you've got absorption there, and then you've got time across the bottom. And if we have a look, you've got a mixture of different alcohols here through the sample. And oops, I didn't mean to do that, but never mind. Okay, and there we can see, so why does propan 1-ol have a longer retention time than ethanol? So if you look at, there's ethanol, it's number 3, that's ethanol. I'm trying to circle that, there's ethanol. And then we've got propan 1-ol, which is this one here. So why will it have a longer retention time? What is the difference between the two molecules? Anybody? You can answer.
Wait,
Michael?
why is there 2 ethanols?
One's ethanol. Number 2 is ethanol.
Oh,
I know my screen is really small, you can hardly see it, but if you look carefully, it says al. So that's an aldehyde. Okay, why would it be longer? What can we see from the name straight away?
Is it because the amount of carbons in ethanol and propanol, the difference?
Yeah, so propanol's longer. So it's going to be a heavier molecule, isn't it? So in that box there, we can write, gosh, okay, let's see if I can fit it in my terrible handwriting now. Right. So number 1 is that propan 1-ol. No, apparently it's refusing to write. Propan 1-ol is longer. No, apparently not. Longer. So it's heavier. That looks vaguely all right, doesn't it? Okay, right. And which compound is present in the greatest quantity? So it's going to have the largest area under the peak. So any guesses? Put your mic on and answer.
wait, are we answering the second question?
Yeah. So which compound is present in the greatest quantity? And if we have a look at here, it can be any one of these.
Propan 1-ol.
Ethanol.
Ethanol, yeah, it's ethanol, not propan 1-ol. Propan 1-ol has the longest retention time.
Okay.
Okay, and retention time tells you ID. And area under the peak, it tells you how much. Okay, so therefore, if we look at this, it's got the biggest peak and it's also got the widest base. Okay, and that would have the greatest area under the curve. And so we're going to say ethanol, if I can write it. Ethanol. And we're going to say, and the reason is, it's got the largest area under peak. There we go. Oh, my handwriting's getting a little bit better. I've worked out that I have to write it bigger. So it looks like a child's writing now. There we are. Okay. Okay. So uses of gas chromatography. It's very sensitive. So you can use very small amounts of substances detected, so you can check explosives if you've got a small sample. You can check drugs even if you've got a tiny sample. And so, you know, when they take hands samples off people's hands or clothing, that can be tested in this way. You can have equipment that is very expensive because it's so sensitive. So it can be very, very sensitive. So separation of pure substances for collection. So because they're taking so much time, there's so much gap between them, there's hardly any overlap. So what happens is I can collect this sample, I can change my sample tube and then collect this sample, etc., etc. So I'd be able to collect pure samples of each substance. Okay, then if I wanted further analysis and proof to make sure that it is what I think it is, because sometimes you can have things that their retention time overlap, even if they're in the same situation. There could be some overlap, or they've got very, very close retention times. So you could add a mass spectrometer. So what kind of information might I get from a mass spectrometer? Anybody? What would it tell me? You can put your mics on and answer.
It would tell you the MR of the molecule.
Yeah, it would. Is that Justin?
Yeah.
Yeah, well done, Justin. So it would tell you the mass, and that could help you in your identification, because if we look at the 1 and 2, ethanol and methanol, their mass would definitely be different, and so you could tell which one's which. Okay, so that's the secondary kind of, as well as the retention time, giving you an ID. The secondary thing that you could do is do a mass spec. Mass specs are very fast as well. So both of these have lots of advantages in that you can do them quite fast, and they're done by the computer. So you just need one person really to run it. Okay, and it also means there's less issues with safety. If it's a toxic substance, you know, that you could weigh, there'd be one person and it'd be the machine that would be contaminated, and then you could run some samples through to clear the machine. Okay, right. Limitations. Many compounds could have the same retention time. So your gas column, gas chromatography does give you a clue, but it doesn't give you proof. So you need other things to get to secondary identify things. Some compounds may not be detected if they are hidden by another more abundant compound with the same retention time. So if you've got two things that have got the same retention time, we've got more of one than the other, you might not get that many molecules of the other, especially if it's in a very low concentration. Okay, if there are no reference times for unknowns, you already have to have a clue of what you think it is, find a pure sample of it, and then put it through the same column so that you can then get a retention time that you can compare to. Okay, so that's some of the limitations. To make identification more certain, so in forensic analysis, they usually have them directly combined with a mass spectrometer. So as this comes out, it goes into a mass spectrometer, and then you get a printout of both things at the same time. And that's quite common. In previous years, we were really lucky. We got to go up to the university, and their ones actually on the same table. They had one. They actually take what's like a dining table, and they take up one. The gas column is on one side, and then on the next side is directly attached to a mass spectrometer, and they look like large photocopiers. And then they're just attached. Some of them attached directly to a printer, and others will send you an email with your graph on it. So depending on who put the sample through. Okay, I'm not sure what time it is. Right, it's 11:30, and I think I've been talking for like 45 minutes continuously. Right, and so I'm gonna, and let me see if we need to move forward. Right, I'm going to leave this page as your task. So page 4 is a task. I would like you to email me a photograph, even from your phone, even if it's not necessarily all correct, that just that you've attempted it. And if you do that before Tuesday, on Tuesday, we can go through the answers. Okay, and let me get rid of this. Right. Hello? Is somebody there? Everybody got that?
I'm still here, yeah.
Yeah, okay. So
You
I'm
are now
assuming you're
unmuted.
still here. I can see you all.
You are now muted.
Right, okay.
What
I
does
can
it mean
also read
by-
all your lovely comments to each other. Sorry, Holly.
What does it mean by label the arrows to describe the main stages? What? I'm so confused.
Okay. So this is the stages in mass chromatography, in gas chromatography. And if we go to the previous, oh, it's kept my lovely. Right. So if we go there, it tells you sample introduced, column separates, detector monitors, recorder. You can just add notes to it, really, is what it means. So what's happening at each phase. And then you've got your mass spectrometry, and then you've got your mass spectrometer. And then explain why it's more powerful than just gas chromatography alone. And we've just been through that. And how can components be identified from their mass spectra? And we've done that in the previous unit, so you could fill that in yourselves, I'm sure. And then that might be something for you to go away and have a look at, have a bit of a research about forensic science when you use gas chromatography and mass spec together. I gave you one example, but if you can find another, that would be really quite useful. Okay, so we've done gas chromatography, and I will send you the PowerPoint as well. And we've done mass spectrometry in the last unit. So is this okay for everybody? So everybody, if you send me a photograph or a copy of just page 4, not the whole thing, then you can show me that you've done it, and then we'll continue from there on Tuesday.
Where's this in for?
Tuesday.
Okay.
Okay, so Tuesday is your next normal lesson.
How are we going to get it? You're going to email it to us.
Oh yeah, so I've emailed you already. I should have emailed you. I will send it again. If Josh, somebody else could, has got it, then they could email it to you as long as you get a copy. I will send it again. Which email address? Josh, have you got my email address?
I presume so.
Okay, so let me just put it on the screen for you.